This lesson deals with lab number 7, an active bandpass filter. In our ECE 202 ebook in chapter 12 on page 33, we defined the general form of a second-order bandpass filter, and it's shown here. So we have a transfer function, in our particular case, an output over an input voltage, and that's equal to some h naught omega naught over q naught times s over s squared plus s times omega naught over q naught plus omega naught squared. Now for sinusoidal signals, s is equal to j omega, so we could substitute that back in for s. And so we'd have j omega times h naught omega naught q naught. Then j squared is a minus 1 times omega squared. J omega times omega naught over q naught, and then omega naught squared. The magnitude is the square root of the real part squared plus the imaginary part squared. But for the numerator, the real part is 0. And so we're just going to have this term multiplying j squared and then square root. This is always a positive number, even if h naught is a negative number. For the denominator, the real part is omega naught squared minus omega squared. We're going to square that, and then add to that the term that multiplies j squared, and then square root. The angle is the angle of the numerator minus the angle of the denominator. The real part is 0, so we're taking the arctangent of the imaginary divided by the real, which is 0, and that's going to go off to infinity, and that's 90 degrees. The denominator, the arctangent of the imaginary part, which is this term, divided by the real part, which is omega naught squared minus omega squared. Now, if h naught is negative, we'll have an additional 180 degrees to add to this. You can clean this up a little bit by dividing by omega naught squared, the numerator and denominator, so it's going to give me a 1. And then I get omega over omega naught squared. And the numerator, dividing by omega naught squared, I get one of these canceling, the omega naught with the omega naught squared. I'm just left with the omega naught q naught divided into omega. So our Bode plot is a plot of the magnitude versus frequency and the angle versus frequency. Now, one point of interest with this particular transfer function is when omega equals omega naught. For the magnitude, this term drops out, and I get the square root of this term squared, which is just this, and then that cancels with this, and that cancels with this. So we just get h naught. At the, we call this center frequency, the value of the magnitude of the gain is just the value of h naught. For the angle, if we let omega equal omega naught, we get a 1 squared here. Again, we take the arctangent of something divided by 0, which is infinity. We'll get 90 degrees again. The difference of those will be 0. Again, if h naught is a negative value, then you can have an additional 180 degrees here. I plotted the magnitude and angle of this transfer function in the ECE 202 ebook in chapter 12 on pages 24 to 25, 33 to 34, and 37 to 39. I'll refer you back to those pages to take a look at the details for sketching the results. We sketched the asymptotes here and then the actual curve. So when omega equals omega naught, or if we're plotting frequency f naught, the maximum gain occurs at that frequency. As you move away from f naught, the gain begins to drop, and there's a point to where the gain drops by 1 over the square root of 2. There's going to be 2 frequencies where that occurs. 1 over the square root of 2, when you take 20 log of that, is a minus 3 dB. So this is dropping 3 dB from the maximum. And the bandwidth is defined as the difference of those 2 frequencies, f2 minus f1. Now I showed in that chapter 12 derivation that that's also equal to f naught over q naught. Now the term that multiplied s in the denominator was omega naught over q naught. So that term, when divided by 2 pi, is the difference of these 2 frequencies. Basically passing everything between these 2 frequencies and pretty much rejecting everything above and below that. As far as the angle goes, when omega is equal to omega naught or f is equal to f naught, all we had was the value of h. And so if that's a positive number, you just get a value of 0 degrees. If it's a negative number, you have 180 degrees. In other words, this whole curve is shifted by 180 degrees. So it's a very special result in terms of finding that center frequency. We're going to use that fact to actually tune in on our circuit. What kind of a circuit could make this bandpass function? Well, in the ECE 202 notes, we showed that you could use an RLC circuit to do that. The problem with an audio circuit is that we're going to use a power supply that's going to derive its voltage from the wall outlet. We're going to do that with a step-down transformer, which uses 2 coils. If we have a coil in our circuit, we can magnetically couple to that transformer, which has a frequency of a multiple of 60 hertz, and that'll show up in our output, and that would have a horrible sound. So we're going to try to avoid using inductors if at all possible in audio circuits. You can see here, this particular structure we're going to analyze in just a minute has got an inverting amplifier here. Now with just R's and C's in these 2 impedances, you can only get real roots. We'll show why that's true in ECE 402. By adding a second feedback path, it's possible to create complex conjugate roots, is what we need for this second order filter. See if we can analyze this circuit in terms of the impedances, and then figure out what kind of components we need to put in these boxes to make this particular case a bandpass filter. Now we talked about analyzing circuits with op-amps in ECE 201, and one technique is to write node equations. How many nodes are in our circuit? Well, besides the ground, there's 1, 2, 3, 4 nodes. So I've got possibly 4 unknowns. I've got an input here, V sub s, and we consider that to be a known. And when we've got feedback here, we know the voltage across these terminals is driven to 0. So this is also a known voltage. In terms of having unknown node voltages, although we've got 4 nodes, there's really only 2 unknown node voltages, and that's V3 and V2. Let's sum the currents at a node that doesn't have a voltage source and see if we can solve for V out over V sub S. Now, the reason we want to pick a node without a voltage source is that this voltage source has a current, but we don't know what its relationship is. Writing a node equation here, we pick up another unknown. The same is true for the output of the op amp. Pick node 3 and node 4 to write my Kirchhoff's current law equations, solve for my 2 unknowns. I'm going to let the current leave the node here. And that means that nothing is entering, so that's 0. That's going to equal the current that's leaving. Current in Z1 is going to be V3 minus V1 divided by Z1 or times Y1. The current in the impedance Z4 is going to be V3 minus V2 divided by Z4 or times Y4. The current in Z2 is going to be V3 minus 0 divided by Z2 or times Y2. And then lastly, the current in Z3 is going to be V3 minus V4, but V4 is equal to 0 divided by Z3 or times Y3. Let's rearrange terms. The things that multiply V1 are just Y1, V1, but that's our input voltage. V1 is equal to V sub S. I'll put that on the other side of the equation. So that's considered to be a known. Then my unknowns are V2 and V3. So what multiplies V2 and V3? Well, V2 is just multiplied by minus V4, and then V3 is multiplied by Y1, Y4, Y2, and Y3. Here's 1, 2, 3, and 4. Just putting them in order by subscript. First equation and 2 unknowns. Second equation, I'm going to do the same thing. Let the current leave the node. Just change the color here. Go in this direction and this direction. Do the same thing. Got nothing entering and everything leaving. Current in Z3 is going to be this node minus this node, so 0 minus V3 divided by Z3. Current going in this direction is V4 minus V2, but V4 is 0 minus V2 divided by Z5. Let's again arrange terms by our 2 unknowns, V2 and V3. So things that multiply V2 is a minus Y5, and things that multiply 3 is a minus Y3. This is in the matrix form, where this term is equal to this term times V2, and then this term times V3. Second equation, I've got 0 is equal to this term times V2, this term times V3. I want to solve for node voltage V2, which is my output voltage. So I'm going to use Kramer's rule to do that. We can solve for V out, which is equal to V2, using Kramer's rule. We'll solve for V2, take the determinant of this matrix, put that in the denominator, and in the numerator I'm going to find the determinant of this matrix with column 1 replaced by the left-hand side of the equation, because that's the column associated with V2. So I have this ratio of determinants. So I have this times this, which is minus Y1, Y3 times V1, and then minus 0. For the denominator, I've got the product of these two, which is Y3, Y4, and then minus this product, which would be a plus Y5 times the quantity, Y1 plus Y2 plus Y3 plus Y4. V1 is equal to V sub S, so I'm going to put that over here, and V2 is equal to V out. So now I have my transfer function in terms of the admittances of the components in my circuit. I'll set that equal to our standard form for a bandpass filter. Now, is it possible to put resistors and capacitors in this slots of the impedances to create this expression? Well, let's start with the numerator. I need S to the first power, so one of these two needs to be a capacitor. Let me make that Y3. Make this equal to a capacitor. Let me make this a little bit larger. I'm just going to do this right on the... So I'll pick this to be a capacitor, so that's the admittance of SC3. Now, to get this to equal a numerator with just S to the first power, this would have to just be a constant. So I'll pick this to be a resistor, R1, which the reciprocal will be G1. The denominator, I've got this determined, and I've got this determined, and I've got this determined. I'm going to need an S squared term, an S to the 1, S to the 0. If I make this the capacitor, then I can't get an S to the 0 term, so I'm going to have to pick this to be a resistor. Pick this to be G5. Then I multiply this out, I get an S to the 0 term, I get an S to the 1 term, and now this term here is going to have to be an S squared, so I'm going to have to pick this to be a capacitor. So I've got S squared, got S to the 1, S to the 1, S to the 0. So this could be either a resistor or a capacitor, but capacitor is a little more expensive than resistor, so I'll pick this to be a resistor. We can do the same technique for a low-pass or a high-pass circuit. Let me go back to full size again. And so it's possible to pick the individual components in this circuit to give me a bandpass function. Now we're going to solve for the actual transfer function. Labeling this on the schematic, we have a resistor for Z1, a resistor for Z2, capacitor for Z3, capacitor for Z4, and a resistor for Z5. Transfer function was minus, because of the inverting amplifier. I had Y1, Y3, Y1, Y2, Y3, Y4, Y5, and then we had Y3, Y4. Now let's rearrange terms here by powers of S. I'll put in the S squared term here. Then I've got R5 divided into these two terms, so that's my S to the first power, and then this times these two terms is my S to the 0 term. And numerators pull out the S, and I've got C3 over R1. Our standard form has a 1 in front of the S squared, so let's divide through by C3, C4. That gives me a 1 times S squared. And dividing this into here, I have 1 over R5, and then C3 divided by C3, C4 is 1 over C4. And then the same thing here, dividing through here, I get 1 over C3. And then dividing this term by C3, C4, I've got this term here, and this is really the parallel combinations of R1 and R2 reciprocal. Likewise, dividing the numerator by C3, C4, the C3's cancel, and I get 1 over R1, C4. This is of the form of a bandpass filter. My bandpass parameters are H0, omega naught, and Q naught, and they are associated with this term, and this term. What I'd like to do is be able to solve for them. In other words, this term right over here is my omega naught squared. This has got omega naught and Q naught mixed together, and this has H0, omega naught, and Q naught mixed together. So we're going to try to use the association of these three terms to extract the value of omega naught, H0, and Q naught. The term omega naught squared was 1 over C3, C4, R5, R1 in parallel with R2. So omega naught is just the square root of that. Now the term H naught is actually in the numerator term, but there's an omega naught over Q naught associated with it. In other words, this term was equal to 1 over R1 C4 on the last page. If I can multiply by the reciprocal of omega naught over Q naught, then I'll cancel those and I'll just get H naught back. But the term omega naught over Q naught was 1 over R5 times 1 over C4 plus 1 over C3. So if I multiply this out, I'll get the value of just H naught. R1 divided by R5, the C4 and C4 cancel, I get a 1, and then C4 over C3. Likewise, the term Q naught is embedded in two terms. It's the term that multiplies S to the 1 was omega naught over Q naught, so the reciprocal of that. If I were to multiply that by omega naught, those would cancel, and I just get the value of Q naught. Omega naught over Q naught is 1 over R5 times 1 over C4 plus 1 over C3 from the last page, and then just flip that over to get Q naught over omega naught. And then omega naught we found would be this expression. If I multiply those two, I'll get the value of Q naught. Let me rewrite this as the square root of C3, C4 times the square root of R5 times R1 in parallel with R2. Let's multiply this term over here. You can write this as the square root of R5 squared. That's going to cancel this numerator R5, and we're left with just an R5 in the denominator, times R1 in parallel with R2. Then this term multiplied here, if you think of this as the square root of C4 squared, would cancel one of the C4s, and I get C3 over C4 square root. And likewise over here, if you think of this as the square root of C3 squared, I would then get C4 over C3. What I've got is an expression now for omega naught, H and Q naught in terms of the 5 components in my circuit. If I were to measure my components very accurately, I could then calculate these 3 filter parameters. What we're going to see later in this lab and the next lab is that we're going to specify filters with these 3 parameters. And then I want to be able to pick these values of components so that I can build my circuit.